talking about what the sun's going to do. When it runs out of central fuel, it'll still have more fuel to burn surrounding the core, but only surrounding the core, not far out. So here is the sun today compared to about how big it will be at its largest as a so-called red giant. So, in other words, so big, right? You know, it's 109 times the size of the Earth. So if you were to make a 1-foot globe to represent the Earth, the sun would be like more than 100 feet across and more than 2 miles away. But this is in correct relative scale for a sun today versus when the sun becomes a red giant after running out of its central hydrogen fuel. So here's a zoom in to the sun today. You got the hydrogen core taking up about 25% or so of the radius, and then there's the envelope surrounding that. When the sun becomes a red giant, it'll be at its maximum, something like 50 times its current radius. And the luminosity will reach up to about 2,000 times what it is now, but all that luminosity will be coming from hydrogen fusion in a thin shell surrounding a tiny degenerate helium core. So that helium core will be only about the size of Earth in the center of a star that has become 50 times bigger than the sun is today, and there will be a thin shell of hydrogen that's fusing into helium via the CNO cycle, because it'll be hotter than the core is today. And at its maximum, it'll be fusing it some 2,000 times faster than the sun is fusing hydrogen now. So, why does that happen? It's because once the sun's core runs out of hydrogen, you will no longer have the fusion reactions that keep it hot enough to maintain the pressure essentially being in equilibrium with gravity. And so as a result, the core will start to shrink because gravity will start winning the battle. So as the core shrinks, what does the virial theorem say is going to happen? We mentioned this sort of idea today, recently, and so forth. So what does the virial theorem say will happen as the sun's core is shrinking after it runs? It's shrinking today, but it will shrink faster when it runs out of hydrogen. Temperature will go up. Why? What's the source of that? Gravitational potential energy, right? It's shrinking, so it's losing gravitational potential energy. The gravitational potential energy is becoming more negative. That gets converted half into radiation, half into thermal energy. So the core heats up as it shrinks, and so that means that it will also be heating up that layer of hydrogen surrounding the core. And so as a result, the hydrogen surrounding the inert helium core will be much hotter than the core is today. Its temperature will climb towards 100 million Kelvin, at which point it will start fusing helium, but we're not there yet. So higher temperatures mean what for the nuclear reaction rate? Faster reactions. And it's the CNO cycle. If you remember, the proton-proton chain goes about like temperature to the 4th power. What about CNO cycle? It's like the 19.6 power. It's like close to the 20th power. It's extremely temperature dependent. So, as the degenerate core shrinks because it no longer has enough pressure support, the surrounding hydrogen gets hotter and hotter, fusing faster and faster. That'll be the primary source of luminosity, is that hydrogen fusing shell surrounding the core. So note that this ties into the assertion that it's the fact that the sun will not keep churning material down into the core to keep being steadily burned that causes it to become a red giant. In other words, it's the fact that you obtain a situation where the core is made of helium surrounded by unburned hydrogen that gives you the situation where you have a shrinking core that heats a thin hydrogen shell up to a high enough temperature. There's hydrogen all the way out to the surface, but in other words, there's a thin shell surrounding the core where nuclear fusion reactions are going on. And they're going on furiously because the temperatures are getting so high as the core shrinks, the tiny little core shrinks. So it's crucial that that the core is radiated here, that it doesn't turn material down all the way into the core from the rest of the star. So if you look at the point that represents the sun on the HR diagram, it does kind of a reverse of what it did when it was collapsing as a protostar. It starts going up near the Hayashi track on the HR diagram because the outer layers become convective due to the flood of all this radiation, and so that causes it to move along the Hayashi track, getting more and more luminous with time because the core keeps shrinking because the hydrogen burning shell produces what? What's the ash of hydrogen burning? Hydrogen fuses to? Helium, right? So the hydrogen burning shell is fusing helium. Helium is denser than hydrogen, and so things stratify in a gravitational field. The denser stuff goes to the center. In the very strong gravitational field in the sun's core at this time, much stronger than it is now, because a very small core like that will have a substantial fraction of the sun's mass in a very small volume. So it'll have very high surface gravity. Very strong gravitational field means that the denser helium being formed in the hydrogen fusing shell will settle into the core. And as we'll see when we study white dwarfs in more detail, a white dwarf, white dwarfs are supported by degeneracy pressure. Okay, the core at this time will not be supported by thermal pressure. It will be supported by electron degeneracy pressure, which again we'll say more about later. So essentially, it'll be like a helium white dwarf in the middle of the star, and white dwarfs have the property that if you add mass to them, they actually shrink in radius. In order to stay in equilibrium, the stronger gravity causes it to shrink to a smaller radius in order to drive up the pressure, in order to go back into balance with gravity. The degeneracy pressure, the rise in balanced gravity, needs the thing to shrink. So, as helium produced in the shell is dumped onto the core will keep shrinking and heating up and driving the temperatures higher and higher. And that flood of photons into the sun's outer layers means that while in the core, pressure is weaker than gravity and it's shrinking, in the outer layers, all that extra radiation will raise the pressure in the outer layers to be stronger than gravity, and so the sun's outer layers are going to swell up. So at the same time that the core is contracting, the outer layers swell up, and the sun becomes a red giant star. So the track it follows in the HR diagram for several 100 million years looks like this, right? So this is saying what? What's the surface temperature doing here to a good approximation as it's climbing up here? It's decreasing. Is it decreasing by much? No. What about the luminosity? Yeah. So what has to be true about the radius? If the temperature is not changing much, but the luminosity is going up, what has to be true about the radius? It's going bigger, right? It's got to get bigger. It's got to have more and more surface area in order to carry off all that extra luminosity if the temperature is not changing much, if the amount of energy coming out of each square meter isn't changing very much. So the structure of the sun as a red giant will be non-burning, no fusion happening, degenerate helium core, so the pressure will be provided by electron degeneracy pressure rather than thermal pressure, which is the primary source of pressure in the sun's core today. And that will be surrounded by a hydrogen-burning shell and a non-burning hydrogen envelope, and as it points out here, the tiny core and shell are not drawn to scale in this schematic drawing, as opposed to a main sequence star where you've got a hydrogen-burning core surrounded by a non-burning shell. So for several 100 million years, the sun swells up and becomes a red giant star, toasts the surface of the Earth, might even probably swallow Mercury, so this will all be quite spectacular. And This figure from the Astronomy 111 textbook kind of shows the idea of this vicious cycle that gets set up. You can kind of join anywhere, so we can say, well, it's okay, so the more compact and more luminous the energy-producing shell becomes, the more the outer parts of the shells of the star swell. Core growth and rapid hydrogen burning feed off each other in a red giant star, because as you're fusing hydrogen and helium faster, you're increasing the rate at which you're dumping mass onto the core, making it shrink faster, grow hotter, causing it to move more and more rapidly up the red giant branch. So if you made a movie, at first it's kind of crawling, but then it moves faster and faster, hundreds of millions, long time by human standards, but if you made a time lapse, going faster and faster. So the idea is, again, we're kind of joining in the middle here, and now we join our shrinking core and expanding star already in progress. Stronger gravity, which leads to greater weight of overlying layers, which leads to higher pressure in the hydrogen-burning shell, which leads to faster nuclear burning, which leads to faster conversion of hydrogen to helium, which leads to faster growth of the helium core mass, which leads to a smaller, more massive degenerate hydrogen core, which leads to stronger gravity, which leads to, right, it's just a vicious cycle. It's a positive feedback loop that keeps accentuating the situation so that the sun and other similar stars grow larger and brighter with time as the hydrogen-burning shell becomes more and more luminous. Note that literally the weight of the overlying layers is increasing. It's not that the mass of the overlying layers is increasing, it's that the strength of gravity at the surface of the core, where the shell is getting higher and higher. If you took Earth's mass and compacted it so that you only had half the present radius of Earth, what would happen to your weight? So imagine shrinking Earth to half its present size. What would happen to your mass if somehow you could just shrink Earth to half its present size while we just stayed where we are? Earthquakes and everything, whatever, we're all out on the surface. God shrinks Earth to half its present size, or whatever, what happens to your mass? Your mass. Mass, nothing. What happens to your weight? Yeah. Goes up by a factor of 4 because the radius would only be half as big. Same amount of mass, half the radius, gm over r squared, becomes 4 times bigger. So as the core shrinks, you're adding mass to it, but not only that, you're shrinking it. And so the surface gravity at the core surface is becoming stronger and stronger, which means that the pressure needed to support the weight, literally the overlying layers are becoming heavier because the gravity that they're experiencing due to the mass of the core is becoming stronger, which means you need more pressure to support that weight. And so another way to understand this, and there, it's not like separate from or anything like that, it goes hand in hand, is you need more and more pressure in the hydrogen-burning shell because it's got to support the weight of the layers above. The weight of the layers above is getting bigger and bigger. And this happens naturally because it's also getting hotter because as the core shrinks, it's heating up due to the conversion of gravitational energy into thermal energy. And so the two things go hand in hand and make the star get bigger and brighter as the hydrogen-burning shell fuses hydrogen faster and faster into helium. Again, note that all of this depends crucially on the fact that you have an inert core in the first place. You wouldn't have that if convection was stirring the entire star up so that you could keep burning hydrogen throughout the entire volume of the star. It's because you run out of hydrogen in the center, but there's still unburned stuff outside that this scenario is able to play itself out. Any questions?
How close is since it goes up by the Hayashi track, how close is that to the original Hayashi?
It's pretty close. It's close. The Hayashi track's a little bit to the right of this, but it's close. Okay. So, here's a schematic diagram for the evolution of one solar mass star. And so, notice up here, 0.6, it's labeled as helium core flash. So, we'll talk about the other parts in a minute, but eventually it becomes hot enough for helium to fuse into carbon. That takes a temperature of about 100 million Kelvin. What temperature is needed for hydrogen to fuse into helium? Do you remember? It's about 10 million Kelvin is where that starts. Yeah, I mean the sun's a bit hotter than that at its core, but 10 million is about the threshold. 10 million Kelvin is what you need to fuse hydrogen and helium as a minimum temperature. Helium requires a higher temperature to ignite. Qualitatively, why do you have to have a higher temperature to ignite helium than you do to ignite hydrogen? Why doesn't hydrogen just fuse in this room? What's keeping fusion from happening in this room? The repulsion of the nuclei for one another, right? The nuclei repel, so two hydrogen nuclei in this room are not going to get anywhere close to one another because they'll veer off course because of the electrical repulsion between them. In order to fuse, they have to move fast enough to get close enough to tunnel and fuse two helium nuclei. What's true about the electrical repulsion between two helium nuclei compared to two hydrogen nuclei? Stronger because each one has two protons in it. So while there's Brunke nuclear physics details, in general terms, the more protons that are in nuclei, the harder it is to fuse them together, where harder means you need a higher temperature in order to do it. So helium fusion requires a higher temperature because helium nuclei repel one another more strongly than hydrogen nuclei do. That's why helium isn't fusing in the sun today. It's not hot enough. But as the core keeps shrinking, eventually its temperature will reach 100 million Kelvin, the ignition point for helium fusion. And as we will see, it will happen explosively. It will go out of control, which is why we call it a helium core flash. In higher mass stars, helium core fusion begins gradually, but in a low mass star like the sun, where the core is supported by degeneracy pressure, at the time fusion begins, it does so explosively. So we'll explain why that is. It has to do directly with the fact that it turns out that with degeneracy pressure, it doesn't depend on the temperature. It only depends on density. So, but let's talk about these other points here. So point 2, or well, point 1 is the zero age main sequence. Then there's point 2 that I labeled from the book. This is I labeled these points from the thing in your book. Point 2 I'm skipping for here. Point 3 in the model that was used to generate the figure here occurs 9.8 billion years after the zero age main sequence for a solar mass star. The central hydrogen is completely depleted, so the proton-proton chain in the core stops, but the core temperature is high enough that hydrogen shell burning continues in a shell surrounding the core, even though the central core itself has run out of fuel. The luminosity then is essentially zero inside the core, because there isn't any fusion happening inside the core. Okay? And remember that one of our equations of static stellar structure was that the temperature gradient, TTDR, was -3 over 4 AC kappa bar Rossland mean opacity rho over T cubed L sub r over 4 pi r squared, but the core's luminosity is 0. Now careful, does that mean that it's dark inside the core, that there's no light in there? No, what does it mean to say the luminosity is 0 inside the core? So if I say that the luminosity is 0 inside the core, imagine you're somewhere inside the core. How can the luminosity be 0 if it's millions of Kelvin and everywhere you look there was bright radiation everywhere? How can the luminosity be 0 if there's incredibly, unbelievably bright light no matter what direction you look? How's that compatible with the luminosity being 0? What is the luminosity?
As long as it's like the flux of the radiation coming out of the
Right,
star.
it's the net outward flux, right? It's the net outward flux. So, what's true about the radiation you see in every direction then, if the luminosity is 0?
They're all going away because it doesn't cancel out.
Well, I definitely have photons hitting. So, I mean, I'm vaporized too, but whatever, you know, omit that part. So, there are photons coming at me from every direction. If I look towards the center and I look towards the surface, compare the brightness when I look towards the center to when I look towards the surface if the luminosity is 0.
The surface is brighter.
But then there would be, so you're saying it's brighter as I look towards the surface, but then there'd be more energy flowing in than flowing out. And that would not be a luminosity of 0. If I'm in the middle of the sun today, if I look towards the core and I look towards the surface, which way is it brighter?
Towards the core.
Towards the core. Because in order for there to be a net flow of energy outwards, more energy has to be coming out from the core than flowing back towards the core from layers further out, right? So that's why there's a temperature gradient in the first place. I need to be looking towards hotter material when I look inwards than when I look outwards, so that literally more and more energetic photons are flowing outwards than flowing inwards. If I were in the middle of the sun right now, oh my God, it's really bright in every direction, but it's even brighter when I look towards the core than when I look towards the surface, because I'm seeing hotter material when I look towards the core than when I look towards the surface. But what if I'm in an isothermal core? When I look towards the center and I look towards the surface, what I see is all the same temperature, because it's isothermal. So what does that mean about the radiation field? What I word applies here? Iso. Describe it. It's
Same.
It's the same in every direction. It's isotropic. It's isotropic. The radiation field is isotropic because the core is isothermal. So the luminosity is 0 because, oh my God, it's really bright in every direction, but there's no net flow of energy. The luminosity is the net flow of energy outwards. So L sub r is 0 is completely, or L is 0 is completely compatible. L sub r, luminosity is function, completely compatible with the core being isothermal and with it being bright everywhere because there's as much energy flowing out as flowing in. That's the point here. There's 0 temperature gradient. dTdr is 0. It's isothermal. In other words, if the luminosity is 0, dTdr must be 0. And if dTdr is 0, T is constant. It's isothermal. This is all together. You're not generating any luminosity. There's no nuclear reactions going on. So the luminosity has to be 0. So I have to see an isotropic radiation field. So that implies that there can't be a temperature gradient. The temperature I see has to look the same everywhere. So it's isothermal. That's the idea there. Okay? Any questions? So the core is isothermal at that point. So at point 4 here, what does that correspond to? That's 11.39 billion years after the 0 age main sequence. So helium added to the core by the hydrogen-burning shell causes its mass to exceed what is called the Schoenberg-Chandrasekhar limit that they came up with in 1942. It's the maximum possible mass of an isothermal core. Now you've got, the book gives a derivation, a hand-waving derivation. It doesn't give quite the right result, but it comes pretty close. One of the homework problems encourages you to think about that. I'm not going to do it here in class. So, degeneracy pressure, it's really fun to try to explain this in Astronomy 111 because it's an inherently quantum mechanical effect. What does the Pauli exclusion principle say? Like, why is there a periodic table? Why, if I have a multi-electron atom, why aren't all the electrons in the ground state?
Because they can only be discrete.
They can only be discrete energies, so why don't they just all go into the ground state and minimize their energy? Like in lithium, what's the electronic structure of lithium? Okay, there's 2 in the ground state, there's 2 in the 1s level, and 1 in the 2s level. in the ground state of lithium? What about, so why don't all three of them go into the ground state? What quantum mechanical rule says that cannot happen? It's related to that. Electrons are fermions. What does that mean? Their spin is 1/2, right? So to be a boson, what's your spin?
So it's been 1,
Or 0, or 2. Integer spin is a boson, half integer spin, 1/2, 3/2, and so forth is a fermion. Electrons, protons, neutrons, they're all fermions. They have spin 1/2. The Pauli exclusion principle says what? In any given orbital, any given quantum wave function, so to speak, you can have at most how many fermions? How many identical fermions? 2. And what has to be true about their spins? They have to be opposite, right? So you can't put 3 electrons in the ground state because that would violate the Pauli exclusion principle. You can only put 2 electrons in the ground state, and they have to have opposite spins. They have to be what's called a singlet spin state. So the next electron has to go into the next lowest energy level, but not the ground state. The reason there's a periodic table is because of the Pauli exclusion principle. Otherwise, everything would just go into all the electrons would sit in the ground state. But instead, they have to occupy higher and higher energy levels because the lower energies are already filled with electrons. That's why there's a periodic table to begin with. So our existence depends on the Pauli exclusion principle. Again, we'll talk about this in more detail when we cover white dwarfs, and you'll also talk about it in thermophysics a lot. But if you look at, say, electrons in a box, a gas of electrons in a box. So if you have an ionized gas, like the core of a star is very hot, so everything's ionized, the electrons are not attached to atoms, they're still confined to the interior of the star, so you can think of them as being stuck inside a box. So remember the infinite square well, right? So you got all these different energy levels available. Imagine that you just stick to one dimension for a minute. When we do the full problem, we'll think in 3 dimensions, but think of an infinite square well, okay? A one-dimensional infinite square well. How many electrons can you put in the ground state? Well, the exclusion principle. 2, and they have to have, I'm just reviewing as we go along, right? So then, if a third electron, so imagine you're dropping electrons in the infinite square well. First one goes into the ground state, because if you want to minimize the energy. Second one goes into the, third one goes into first excited state. Second one goes into, third one goes into, those are 3 and 4, right? Those are the third and fourth electrons. The fifth one goes into second excited state. The sixth one goes into, and then the one after that goes into third excited state, and so forth. So the ground state configuration is you just keep, you imagine dumping electrons in, and each electron goes into the lowest energy level that still hasn't been occupied yet. That's the ground state configuration. And if you think about it, remember absolute zero is the state of minimum energy. So at absolute zero temperature, they would all be arranged so as to be in the lowest energy states that are not occupied. So you would fill up energy states until you stopped adding electrons, and then there'd be unoccupied states above that because you didn't add any more electrons. If you keep adding electrons, you're forced to add them to higher and higher energy levels. So the greater the density, in other words, the more electrons you pack into the well, the higher their overall energy is, because the Pauli exclusion principle forces them to occupy higher and higher energy levels. So, classically speaking, 0 Kelvin corresponds to all molecular motion ceasing. There's no energy. But when you throw in quantum mechanics, if you're dealing with fermions, even at absolute zero temperature, there's a lot of energy there because of the Pauli exclusion principle. And what that means is that those electrons in the well exert a lot of pressure because even at absolute zero, at zero temperature, they are forced to have high energies by the fact that all the lower energy levels have already been occupied. Now, if the temperature is not equal to zero, then electrons will jump up into higher energy levels. You won't have all the lower levels occupied, they'll occupy higher energy levels. At low densities, you get ordinary gas pressure, which corresponds to the electrons are not all in their lowest possible energies because of the fact that you put heat into the system. But if you have high enough densities, then what happens is that you are forcing high energy levels to be occupied by the fact that you pack so many electrons in there that by the Pauli exclusion principle, they're being forced to occupy high energy levels. And if the density is high enough, then what you get is a situation where electrons have much higher energies than you would expect from their thermal energy, from the temperature alone, classically speaking. They're forced into high energy levels by the Pauli exclusion principle. And that's the key to the idea of electron degeneracy pressure, or for that matter, neutron degeneracy pressure. Degeneracy pressure exists because the density has become high enough that most of the electrons or neutrons or whatever occupy energy levels such that their kinetic energy is much higher than you would expect from just like 1/2 kT or whatever. Okay? And in the sun's core, at this stage of its life, the core will be so dense that most of the electron's energy will be due to the Pauli exclusion principle and not to the temperature. That's the idea here. So that's what we're dealing with here. An ordinary example, if you will, of degeneracy pressure is the stiffness of metals. So in a metal, the electrons do not act as though they belong to the individual. The outer shell electrons do not act as though they belong to individual nuclei. When the outer orbitals overlap one another, it turns out that they start occupying the entire volume of the metal. The inner shell electrons belong to individual nuclei, so to speak. They're localized on individual nuclei. But the outer shell electrons are in orbitals that spread throughout the volume, and so they're free to move, and that's what makes them conduction electrons. And furthermore, at room temperature, they're degenerate. In other words, they have much higher energies than you would expect from just classical thermodynamics 1/2 kT kind of configurations or 3/2 kT kind of configurations. So it depends on the metal, but the kinetic energy of the electrons in the metal is on the order of what you would expect from classical thermal physics for a temperature like 100,000 Kelvin or something like that. That's why the metal is so stiff, because the electrons are exerting very high electron degeneracy pressure. So, back to our story here, there's a limit to how much mass an isothermal core is able to support. And it turns out that the mass of the isothermal core divided by the mass of the star is about 0.37 times the mean molecular weight of the envelope divided by the mean molecular weight of the isothermal core squared. And that shouldn't be obvious to you, it's just that works out to be what the maximum mass is. For example, if you start out with an initial composition of 70.8% hydrogen, 27.2% helium, 2% metals, then the envelope's mean molecular weight works out to be 0.61 in those conditions, and the core 1.34, we assume pure ionized helium right before we came up with 4/3 for the mean molecular weight for pure ionized helium. That gives the mass of the isothermal core, the maximum possible mass being about 8% the mass of the sun, about 80 times the mass of Jupiter, roughly speaking. So, partial degeneracy in the core means that a solar mass star can actually exceed this. This would be under the conditions of an ideal gas. That would be the maximum amount of gas that thermal forces support. Degeneracy pressure is above and beyond thermal pressure from the standpoint of degeneracy pressure is stiffer than ordinary thermal pressure because the particles have extra energy due to the Pauli exclusion principle, if you will. They've been forced up into higher energy levels. And so that actually raises the limit for the sun to like 13% of its mass instead of 8% of its mass. When the so-called Schoenberg-Chandrasekhar limit is reached, that's what we define to be the end of the main sequence mass for stars less than 1.2 times the mass of the sun. When the core exceeds, due to the dumping of helium onto it, when it exceeds that, that's when the core is going to start to shrink on the Kelvin-Helmholtz time scale. That's when pressure is no longer strong enough to balance gravity and starts to contract as a result of that. Core temperature increases by the Virial theorem, heating the hydrogen burning shell, causing the luminosity to increase and the envelope to expand and cool. In other words, this is when that vicious cycle begins. This is when the star starts accelerating its climb up the red giant branch. Okay, any questions? All the stuff about degeneracy pressure will make more and more sense as we go along and get into more force and so on and so forth. But right now I just want you to qualitatively understand it's because of the Pauli exclusion principle forcing the electrons to have much more energy than they would at high densities due to just ordinary classical thermal physics. Okay? Point 5, right there. Notice that's where it's kind of, oh, I'm ready to start climbing up the Hayashi track. Point 5, about 11.64 billion years after the zero-age main sequence, H minus dominates the envelope capacity, deep convection ensues, and so it starts climbing the red giant branch along the Hayashi track. Because the H minus ion, remember, can be ionized by any visible photon, infrared photon shorter than a certain wavelength, any ultraviolet light photon. So the H minus makes for high opacity, which makes it hard for radiation to transport the energy, which makes convection the more efficient mechanism for energy transport. So the envelope becomes convective, and that's exactly the condition. When you've got deep convection, that's when you intend to climb the Hayashi track. And then point 6, 12.27 billion years after the zero-age main sequence in this model. The core gets to 100 million Kelvin and ignites the helium flash. Okay, so any questions? As we already mentioned, the stiffness of a metal is an everyday example of electron degeneracy pressure. When the sun is its final remnant, it will be a white dwarf supported by electron degeneracy pressure, similar to what makes a metal stiff. So here's our red giant in cross-section, and so we've got an electron-degenerate helium core. It's supported by degenerate electrons, surrounded by a hydrogen-burning shell, non-degenerate envelope, non-burning, I meant to say envelope. The weight of the overlying layers of the stars is supported by degeneracy pressure of the sea of tightly packed electrons. And the helium nuclei are just kind of floating in that degenerate electron. See, they are not degenerate. They are exerting ordinary gas pressure, but that's not nearly as much as the pressure being exerted by the electrons, which have been forced into much higher energies by the Pauli exclusion principle. So helium nuclei are free to move about within the electron sea, acting like a normal gas within the degenerate electron gas. Almost all the pressure is being produced by the electrons. The helium nuclei are just floating around in the electron sea, if you will. When you reach 100 million Kelvin, you can start fusing helium into carbon, and it's a two-step process. So it's called the triple alpha process because alpha particle is a name for a helium nucleus by itself. So it begins when two helium-4s fuse into a beryllium-8, but beryllium-8 is very unstable. It will not hold together, and so it will quickly fall apart unless another helium-4 nucleus comes in just in time and smacks into it and forms carbon-12. And then the carbon-12 is formed in an excited state, which decays to the ground state, gives off a gamma ray. So the energy released in the fusion reaction is carried off by both the kinetic energy of the carbon-12 nucleus, which then gets distributed to the rest of the gas by collisions and by a gamma ray. Okay, so carbon fusion, fusion into carbon, fusion of helium into carbon takes place by this process, but it does so explosively. So let's first talk about why the sun is not a bomb today. Why the sun doesn't just blow up. This is a good thing, because we would not be having this conversation if the sun was going to blow up. So, the sun has negative feedback today. Remember we talked about clouds being a climate control mechanism for Earth, so to speak. The sun has a kind of climate control mechanism in its core that we can call the solar thermostat. It's broken in the degenerate core, and so it doesn't work, but let's talk about what happens in the sun today. So, suppose that for whatever reason the sun's core temperature were to rise a little bit. What would that do to the rate of the nuclear reactions? It would increase them, and so the fusion rate would increase. You'd be releasing more energy by fusion. That would drive up the pressure in the core, which would make the core expand. And if you expand, you're converting thermal energy into gravitational potential energy, and bring the core back down again. So in other words, we have negative feedback. If the fusion rate, if the core temperature were to go up, the rise in the fusion rate, it turns out, would raise the pressure enough to expand the core back and cool it back down and go back to normal. And it would flip the other way. If the core temperature were to drop, the reaction rate would drop down, the core would shrink, tend to start shrinking. That would heat the core back up again and restore things back to normal. So things are stable. And the reason they're stable is that the core, about 90% of the pressure in the sun's core today is due to ordinary thermal pressure, about 10% degeneracy pressure. Thermal pressure depends on temperature, right? According to the ideal, ordinary thermal pressure, according to the ideal gas law, P is nKT. So if the temperature goes up, the pressure goes up. Degeneracy pressure isn't like that. Degeneracy pressure is essentially independent of temperature. It only depends on density, it doesn't depend on temperature. So, when the helium flash begins, I forget what my next slide looks like here. Yeah, okay. I'll just put it here. When the helium flash begins in a low mass star like the sun, the core is degenerate. So, helium starts fusing into carbon, and that releases energy. What will that do to the temperature of the core? If I light a fire inside of a furnace, what happens to the temperature of the air in the furnace? It goes up, right? So in other words, the fusion is releasing energy into the surrounding material, right? So fusion starts of helium into carbon in the core, so the temperature rises. The core is degenerate, so as the temperature rises, what happens to the pressure? It's degenerate. So what do we say for degeneracy pressure? It doesn't depend on the temperature. It's because of the fact that the electrons have most of their energy due to the Pauli exclusion principle. Their energies, most of the electrons have energies that are way higher because of quantum mechanics than you would expect due to classical thermal physics from the temperature. So you increase the temperature, that doesn't change the pressure because most of the electrons are really high energies anyway. When you raise the temperature, a few electrons get promoted to higher energy levels as a result, but still most of their energy, most of the electrons' energy is due to the Pauli exclusion principle. So as a result, to a really good approximation, the pressure does not depend on the temperature for a degenerate gas. So helium fusion starts, the temperature rises, but the pressure remains the same. So can the core expand and cool? No, the core does not respond by expanding and cooling. So the temperature rises, what will that do to the rate of the helium fusion? It goes up. So it gets even hotter. Does the pressure change? No. So it got even hotter, so what happens to the nuclear reaction rate? It got even faster, which makes it even hotter, which makes the reactions go even faster, which makes it even hotter, which makes the reactions go even faster. In other words, when you don't have the pressure depending on the temperature, because the core is degenerate, it's going to act like a bomb. It's going to go out of control. Because once the reactions begin, the energy they release makes the reactions go faster, which releases even more energy, which makes the reactions go even faster, which releases even more energy. So it spirals out of control. There's no thermostat. The thermostat is broken in a degenerate core. The sun's core today is not degenerate, so it has a working thermostat. It will expand and cool if the temperature, if the nuclear reaction rate were to go up. But that thermostat is broken in the degenerate core of a low mass star when it becomes hot enough to fuse helium. The result is that the helium burning begins explosively in a helium flash. And so for a couple of minutes, it turns out that the helium reaction rate just keeps climbing and climbing and climbing. The fusion rate keeps climbing. So that for a brief while, the core of the star is producing more power than all the other stars in the galaxy it's in put together. So for a brief, glorious moment, the sun's core will be outshining the rest of the Milky Way galaxy during this so-called helium flash. It turns out that computer models can't handle it. Conditions are changing so rapidly in the helium flash. Normally, our computer models evolve much more rapidly than the actual star does, right? It wouldn't do us any good if it took us 20 billion years to calculate the sun's 10 billion year evolution. The helium flash is such that, and I read this some years ago, so it's probably a little better now, but at one point I read words to the effect of that it would take 1,000 years to simulate 1 second of the helium flash with current computer technology. So we actually still are not able to simulate the helium flash in computers in detail. But on the other hand, because you would need too fine a resolution. Conditions are changing over such small spatial scales, you'd need too fine a resolution. Computations would take too long. But the idea is, once you reach this point right here, the so-called tip of the red giant branch, you have the helium flash. There's runaway helium burning, the degenerate helium core explodes within the star, but eventually the temperature becomes so high that the electrons become thermal again. In other words, their energy is so hot that their energies become being due to how hot it is as opposed to being due to the Pauli exclusion principle. And when that happens, the thermostat kicks in. In other words, the pressure starts to rise, the core expands, and the helium burning rate settles down to a nice steady level. And that's the next phase of the star's evolution. So after the helium flash, the sun will settle onto what's called the horizontal branch of the HR diagram. It's called the horizontal branch because stars that are fusing helium steadily in their cores live along a nearly horizontal line on the HR diagram. And it is a sort of helium fusing main sequence, if you will. In other words, now you've got core helium fusion instead of core hydrogen fusion. And so it's a kind of helium fusing main sequence, which turns out to be at nearly constant luminosity no matter what. So you get a horizontal line. So the sun will become what we call a horizontal branch star. The name coming from where they are on the HR diagram. And so the structure then becomes, you have a stable helium burning core, surrounded still by a hydrogen burning shell and a non-burning hydrogen envelope. So notice the first stage was hydrogen fusion in the core. That's what we call when the sun's fusing hydrogen in its core, that's the, what stage? Main sequence. Then it switches to hydrogen fusing in a shell surrounding the core and becomes a red giant. Then it starts fusing helium in the core and becomes a horizontal branch star. Is it going to be able to now fuse helium in the core for all eternity? No. There's only so much helium in the core, it's going to run out. So when it ran out of hydrogen in the core, it switched to fusing hydrogen in a shell. What do you think is going to happen when it runs out of helium in the core?
Fuse helium in the shell.
It'll fuse helium in a shell, and when that happens, we're going to get kind of, skip this to just kind of the end note today. When it runs out of helium in the core and starts fusing helium in a shell, we'll get a kind of repeat performance of what happened when it switched to hydrogen fusion in a shell. In other words, the now degenerate carbon core will shrink and get hotter and hotter and drive the helium fusion shell to higher and higher temperatures and thus higher and higher luminosities. And so once again, the flood of radiation will cause the outer layers of the star to expand, and the sun will go into a second red giant phase, which is called the asymptotic giant branch phase. And the reason it's called the asymptotic giant branch is because it once again climbs the giant branch, and this is a really stupid name, but we're stuck with it. So it's in math, if one curve approaches a limit, if a curve approaches a limit, it asymptotes to the limit. So the track on the HR diagram is asymptotically approaching the Hayashi track, the red giant branch. So it's an asymptotic giant branch star, an AGB star. Whoever came up with that name was like, oh God. So the Astronomy 111 text, they call them more descriptive names. They're not standard astronomer names, but we really ought to adopt them. The Astronomy 111 text says main sequence, red giant, core, helium core fusion star for what we call a horizontal branch star, and it calls this a double shell fusion star because you're fusing helium surrounding the inert carbon core, and you're still fusing hydrogen surrounding the helium fusion shell. Okay, so here's the take home. Here's what I definitely want you to remember here. There's a logic to this. It's easy to get lost in the details, but there's a flow to this. So think of it like this. Notice when the sun is a horizontal branch star, even though it now has two sources of energy, helium burning in the core, hydrogen burning in a shell surrounding the core, it won't be as bright as it was as a red giant. It'll be brighter than it is today, like 50 times brighter than it is today, but it won't be nearly as bright as it is as a red giant. And that's because the helium-burning core has expanded and cooled compared to how hot the core was before. And so, in particular, what I should say is the hydrogen-burning shell is now pushed further away, and it's not as hot in the hydrogen-burning shell as it was when the star was up near the tip of the red giant branch. So the rate of fusion in the hydrogen-burning shell is way lower than it was when the star was a red giant. So the combined rate of energy generation by the helium-fusing core and the hydrogen-burning shell when you're on the horizontal branch is much less than the hydrogen shell alone was producing when the star was a red giant. So notice, when there's hydrogen core fusion, you're on the main sequence. You are not a giant. When there's helium core fusion, you're on the horizontal branch. You are not a giant. But when you're fusing hydrogen in a shell, you're a red giant. When you're fusing helium in a shell, you're an asymptotic giant branch star. You're a giant again. So, rule number one, core fusion, not a giant. Shell fusion, giant. Principle number two here. Here's the rhythm. You burn something first in the core, then in a shell surrounding the core. So it goes like this. The sun's life in a nutshell is hydrogen core, hydrogen shell, helium core, helium shell. Right, got it? Hydrogen core, hydrogen shell, helium core, helium shell. Now, in parentheses, once a shell starts, it stays. So in other words, when I say hydrogen shell, that's going to keep going, except I won't make it part of the official, what I describe it. So in other words, when I say helium core, also hydrogen shell. And then helium shell, also hydrogen shell. The hydrogen shell sticks around. I just stop. I don't keep saying it. Right? So hydrogen core, hydrogen shell. Helium core, helium shell. And meanwhile, it's main sequence, red giant, horizontal branch, asymptotic giant branch. So in other words, not a giant when it's in the core, giant when it's in a shell. So it's really not hard to get this down. It's really not, if you think about it, okay? So I would want you to be able to kind of fill in the steps. In other words, tell me what's fusing where here. Hydrogen where? Core. Now where? What's fusing and where? Hydrogen shell.
Helium.
Or helium shell, right? That's the rhythm, right? It goes, so main sequence, red giant, helium flash, horizontal branch, asymptotic giant branch. And hydrogen core, hydrogen shell. Helium core, helium shell. It's not hard to remember if you get kind of the rhythm, literally, of what's going on. And then the next thing is poof. As in, the helium burning shell is unstable, it's subject to flare-ups, we'll say more next time. That blows the outer layers off into space and leaves the inert carbon core left behind as the final white dwarf remnant of the star. So, the history of the sun, hydrogen core, hydrogen shell, helium shell, poof, white dwarf. I think you should literally, we should make a song or something. We're not going to make a song. But that's the sequence. Burn that into your brain. That's what I want you to take away. Burn that into your brain. Okay? So, if you think about it, if you concentrate on it, it's not hard to get it. It really isn't. Yes?
What is the helium flash again?
So the helium flash is the explosive emission of helium burning in the degenerate core of a low mass star like the sun. So the core is degenerate when it reaches the temperature that helium fusion begins. So that means it will go out of control because degeneracy means that temperature and pressure are unlinked. So helium fusion raises the core temperature, but not the core pressure, which means the core can't expand and cool down. And so as a result, the helium fusion goes faster and faster because the helium fusion reactions, once they start, they make it hotter, which makes them go faster, which makes it hotter, which makes them go faster. That's why a bomb blows up. In other words, if you light the fuse on a bomb, once it hits the explosive, the burning of the explosive makes it hotter, which makes the reaction go faster, which makes it hotter, in other words, it's self-propagating. Not necessarily hotter, but at least the energy released is burning more and more of the material, which releases more and more energy, which burns more and more of the material, and so it rapidly goes out of control. That's how a bomb works. It's explosive precisely because of the fact that the reaction just rapidly goes out of control. And so if you have a degenerate gas that can reach the point of ignition of nuclear reactions, it will go like a bomb. The reactions will go out of control. Unlike in the sun today, it's not a bomb because there's a relinking between pressure and temperature. If the temperature goes up, the pressure goes up and would cause the core to expand and cool things back down again.
I guess my question is, how does that relate to, it's big, it swells up like a red giant, and then all of a sudden, back up. Is that?
So you're talking about why does it shrink after the helium flash? So the helium flash is over in a few minutes, okay?
So it's just a big flash.
It's a big flash, but it turns out the outer layers of the star are able to contain it. You wouldn't know it from the outside. You don't see anything from the outside because, remember, how long does it take for energy to get out of the sun's core out to the surface, roughly speaking? Yeah, hundreds of thousands, like a million years. The flash happens like in a couple minutes' time. Not nearly enough time for those photons to get out to the surface. So from the outside, you don't see anything. The helium flash is over when the core, after a couple of minutes, reaches temperatures big enough for it to expand and cool down. And so when the core expands and cools down, there's not as much energy flowing out of the outer layers anymore. So the pressure, the luminosity goes down, so the pressure is not as big in the outer layers, and so they contract because there's not as much pressure on them. So they contract and heat up, and so the star becomes less luminous, smaller, but hotter than it was as a red giant star. And so this happens pretty quickly. Pretty quickly shrinks and becomes a horizontal branch star after the helium flash occurs. Yeah, good question. We don't see the helium flash because the core is surrounded by the rest of the star. On the other hand, a white dwarf with a companion or that collides with another white dwarf, its interior temperature can go above 600 million Kelvin, which is the ignition point for carbon, and there's nothing to contain the explosion. It's degenerate, so it's going to go like a bomb. It blows itself to shreds and becomes what we call a type 1a supernova. A very important type of supernova. Type 1as are exploding white dwarfs. The helium flash is kind of like a supernova that's got a star surrounding it, and so it doesn't. The outer layers are able to contain it, so you don't see anything from the outside other than you see the star shrink down in size afterwards. But there's nothing spectacular that happens from the outside. Unlike if the envelope weren't there, if the helium flash happened with no envelope there, it would be a type of supernova. It would blow up like it would be a supernova in that case. Any other questions? All right, the end for now. Boom!